Hi there, photography enthusiast. It's me Satya. Today let's discuss about magnification factor. This video is going to be math heavy. You could have guessed it from my t-shirt. Magnification factor in microscope is defined as the ratio between the actual size of the object and the size at which it appears to our eyes. The same definition cannot be directly applied to photos because the real world objects appear much smaller in the sensor. Hence, in photography, magnification factor is defined as ratio between two different focal lengths. Let's say we capture a subject at let's say 50 mm focal length, and then the same subject is captured at a different focal length, let's say 75 mm. Now the size of the object that appears in the image is compared to say the relative magnification between this two focal length. Let's look at an example. We have a subject, and then the camera is positioned here, and it's mounted with a lens of focal length 50 mm. Now we capture the subject, and then in the resulting image, if we draw a closed bounding box around it, and the dimension of the bounding box is 1000 pixels height and then 500 pixels wide. Let's say, keeping everything constant, just mount the camera with a different lens of focal length 75, keeping the distance between the subject and the camera constant and everything else constant. In the new setup, take a new image. Can we identify the dimension of the uh, subject in the new image? Yes, we can figure it out without actually taking the image or actually doing the experiment and measuring its size. It's possible. They are driven by the math expression f1 by f2 equal to dim1 by dim2. Here the subscript 1 represent setup 1 and subscript 2 represent setup 2. F is the focal length and D is the dimension. Dim1 and dim2 represent 1D dimensions, uh, say width and height. Out of these four variables, if we know three, one of that could be figured out. So in our case, we know the focal length f1 and f2, and we know the dimension. We have the previous image. From that, like we measured the previous image and it got a dimension of 1000 cross 500, and in dim2 can be figured out. Now in the resulting image, if we rearrange and do the computation, height of the image is going to be 1500 and width of the subject is going to be 750. This would be helpful in setups where kind of wild photography or bird photography, where like should you upgrade your lens. Let's say you have a lens of focal length 300, should you upgrade to 400? If so, if you upgrade to 400, how big your subject would appear? Right now it might be very tiny. By having a longer focal length like 400 or 600, the size of the subject is going to increase, and you can figure out how big the resulting subject size could be. Now if you want to compute the area, because images have two dimensions, and then if you want to compute the area, it's going to be square of the individual dimension increase. The ratio between the focal length in our example is 1.5. So individually, linearly it increased by 1.5, but if the final pixel, the area occupied would be 1.5 square. Let's say our factor is 2. Let's say you were previously shooting with 300 mm and now you want to upgrade to a 600 mm lens. You doubled the focal length, then the individual dimensions will also double, but the area would be 4 times. To test this theory, I performed this experiment. I created a rectangle and then drawn this 45-degree line in both directions, as well as included a perfect vertical and horizontal line. Printed this in a paper A4 sheet and then tried to photograph this subject with a different focal length starting from some 70 mm to 350 mm, keeping the distance between the camera and then this subject constant. Later, from the resulting image, and then try to figure out the dimension of the subject at a different focal length. Here is a table that shows width and height of the subject at various focal length. Table 1 represent the dim 1 and dim 2 ratios, dimension 1 and dimension 2 ratios. Table 2 represent the focal length ratios, and table 3 represent the error. Why we should have error? When I introduce the expression, I haven't spoke about the assumptions. One of the assumption is, or major assumption is, the plane of the subject and the plane of the sensor in the camera should be perfectly parallel. Even if there was a slight deviation in these two planes, when we change the focal length, because of the perspective change, we might end up with a different dimension. It's going to be very pronounced when we are working at a very long focal length like 350 or so. And there is another error that is introduced by not having the subject at the exact center of the sensor. This is because when we change the focal length and then the subject is not exactly at the center middle of the sensor, then it also introduces a perspective change. To minimize the error, I tried to align the grid lines in my camera viewfinder with the subject. I did my best. Still, you can see there is a slight difference between both of them. It was really a very difficult task. A minor change in the camera position or angle is also leading to a huge difference in the alignment. Even pressing the shutter button is leading to slightest change, and then I was very careful in taking each of the exposure during the experiment. Because of these conditions, we will have a minor error, and let's check the distribution of the error to see whether they are real practical errors or they show the flaws in the expression. By looking at the plot of the error, we can see the error ranges from low to high at every focal length, and there is no correlation, direct correlation between the error and the focal length. So we can conclude that this error or practical measurement error, not any flaw in the expression. Perform a similar computation for the other dimension, height of the images too. Now an interesting question arises. Should we always have two images to compare their magnification factor? Can we predict the size of an object with other factors, how much big it would appear in the final image? Is it possible? Yes, it's 100% possible, and there are physical models and the expression that governs how big the subject appear in our image, and that is driven by the expression capital H by capital D equal to small h by f. Here, capital H is the size of the object in the object space. In the real world, how big it is. Again, it is a single dimension. And in D represent the distance between the subject and the sensor, how far away these two are. And in small h represent height of the object in the sensor, and in F represent the focal length. Here there is a trick. We know h in terms of pixels. We have to translate that into again millimeters or meters, because the capital H is measured in one of this unit like meters or millimeters. So the pixel should be translated into millimeters, and that is possible. Again, we can use another ratio to compute that. It's like based on the size of your sensor and in your pixel, megapixel that is available in the sensor. With that, we can translate small h in pixels to millimeters. Again, in this expression, we have four variables. If we know three of them, we can figure out one. So I choose to predict or figure out the value of capital H provided we have rest of the three. It can be done in another way too. Knowing capital H, we can figure out small h That is also possible. It's completely up to us. So I choose to figure out capital H provided rest of the three variables, and then finally measured the rectangle using a scale in physical world and try to compare the prediction error between these two. Here is a plot of the error. Again, we can see it is not correlated with the focal length, and then it's a particle measurement error. Hope you like this video and enjoy the computation along with me. If you want to see more of this kind of video, the mathematical aspects of photography, please let me know in the comment. Also, if you want to know math beyond any other aspects of the photography, let me know in the comments. I will try to make a video around it. Thanks for watching. We'll meet you in another video. Bye.